Okay, so thanks very much for showing up today. For those of you that don't know me,
You're welcome.
I'm a final year PhD student, Jasmine Gill, and it's my absolute pleasure to introduce Adam Burrows today to give a talk on the emerging theory of core collapse supernovae explosions. Now, before I hand over the mic to Adam for posterity, I'd like to just read you folks his biographical sketch. Adam Burrows is currently a professor of astrophysical sciences at Princeton University. He received his undergraduate degree in physics from Princeton and his PhD in physics from the Massachusetts Institute of Technology.
Sorry.
His primary research interests are supernova theory, exoplanet and brown dwarf theory, planetary atmospheres, computational astrophysics, and nuclear astrophysics. Well known as a pioneer in the theory of exoplanets, brown dwarfs, and supernovae, he has written numerous fundamental and influential papers and reviews on these subjects during the last 35 years. He has collaborated with more than 250 co-authors on more than 400 papers and given more than 400 invited talks and colloquia. Oops. He is a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences, a fellow of the American Association for the Advancement of Science. Oops. A fellow of the American Physical Society, the Beatrice M. Tinsley Centennial Professor, a winner of the Arbitsuman Prize, and a former Alfred P. Sloan Fellow. He was also the founding director of Princeton's Planets and Life Certificate Program, a former member of the Board of Trustees of the Aspen Center for Physics and fellow of the Princeton Center for Theoretical Science, PCTS. In addition, he is a past chair of the Board on Physics and Astronomy of the National Research Council of the National Academy of Sciences, was the BPA liaison to the 2010 Decadal Survey of Astronomy, and has been a consultant for the American Museum of Natural History in New York. Almost done. He has served on the Committee on Astronomy and Astrophysics of the NRC, on the NRC Rare Isotope Science Assessment Committee, on the Subcommittee on the Implementation of the DOE Long Range Plan for Nuclear Physics, as the chair of the Kavli Institute for Theoretical Physics Advisory Board, as the co-chair of NASA's Universe Subcommittee, as the chair of NASA's Origins Subcommittee, as a co-chair of NASA's Strategic Road Mapping Committee, etc., etc., etc. It is my absolute pleasure once more to introduce Adam Burrows. Adam, please take it away.
Thank you. I might as well just stop here if I'd done all that. Jeez. What I hope to communicate to you today is progress that's been made in a problem that has been with us for more than 60 years in the theoretical context, which is the nature and character and mechanism of core collapse supernova explosions. Of course, as people know, it's in this context that many of the elements of nature are produced and ejected. It's in this context that neutron stars and stellar mass black holes are produced. But such as the complexity of the problem, that it's taken many, many years to even convince oneself that one has a handle on it. I want you to think right now what you think the mechanism of explosion is. What is your mental picture of the explosion? I'll give you 3 seconds. So what I'm asking you is, what is your prejudice? And what I'm going to try to do is blow you away. Now, of course, in doing this, I need the help of collaborators. Tianxu Wang and David Vartanian I want to give a shout out to. In particular, they've been longtime collaborators and my graduate students, now postdocs, both in California, in fact. And of course, to funders, past and present. And so I'm going to show some eye candy first. This is stuff that is not associated with my work, but it's just a motivation. This, of course, is 87A, and there are complexities associated with this, but I want you to note that these things aren't spheres. This is the explosion. This is Cas A. This is J2ST data with a composite from, in fact, the X-ray data just shown to indicate it as well that the distribution of the elements, the distribution of the matter is very asymmetrical. And so these things are not spheres. All right. So the other slides that I skipped are just, again, eye candy showing you the pictures of supernova remnants. And in these contexts, these things are very asymmetrical. And we're trying to explain in some great detail all the observables. What are the observables? The energy of the explosion, the correlation between the progenitor and the neutron star or black hole that might be birthed, the nucleosynthesis. These things are given kicks at birth. The neutron stars are some of the fastest population in the galaxy. Where did these kicks come from? Asymmetrical explosions could explain it. And so what we want to do is actually to explain the things that observers are going to see. And for many, many years, we've been, as a theoretical community, in isolation, trying to divine the actual physics with numerical simulations, fairly detailed calculations. And that has separated us in some small measure from the observer community that is discovering supernovae and profusion. And so the goal of the future is to connect the emerging supernova theory with the plethora of data that are available now to see how you can explain physically what's going on. And so to do this, we've developed from scratch a new code called Fornax that has allowed us to do not one 3D simulation. Again, these are expensive, 100 million CPU hours per model, but 30, not to just a few seconds after the bounce. That's a long time for the tradition, because every time step is a microsecond. You can do the math. But for many seconds, to asymptote the final state, because people who've calculated in the past have calculated up to a point that they could afford, but it was before we figured out anything. The explosion energies were not determined then. You have to calculate for much later. The reason for that is that these things are neutrino-driven, and the neutrinos have to stay on for a long period of time to build up the energy, and I'll show that. And so what we've been able to do is calculate for more than 200 model seconds, which is more than the rest of the world combined. Most of the models explode naturally in the 3D context with the beta physics. This is a new thing to some people, but we've been doing this for 5 years. So in my humble estimation, the problem, I believe, is solved qualitatively, not quantitatively. Because quantitatively, these are chaotic. There are all sorts of details. It depends on stellar evolution. Depends on rotation. We don't know the inner rotation. Binary interaction. We have our work cut out for us. But at the very least, we're at a crossroads where we can look forward to actually integrating all these things that are directly relevant to everything that is associated with supernova in the astronomical realm. What are those things? Well, let me just give it a basic thing in the beginning. Low mass progenitors above 8, 9, 10 solar masses, something like that, generally are more spherical. I'm going to show all this. They leave behind low mass neutron stars. They have lower explosion energies. There's a lower amount of nickel-56, a major radioactive species produced in this context. They have lower kick speeds, etc. The higher mass progenitors are the opposite. They're more energetic explosions. They take longer to explode, and that's backwards from what you might have thought. Quicker explosion, you get more energy, it's just the opposite. Let's just hope I don't crash again. Or if I crash again, it's the last time. Okay, now again, this is just words. I'm going to get into some of the more detailed stuff, but I want to give you a basic background. The initial progenitors are they're not settled. The massive star stellar evolution is not a solved problem. I can explain that. There's binarity effects, there's angular momentum transfer, mass loss, all these sorts of things are still in play. and they have an effect on the final product. So what I'm going to show you is single-star evolution from one group, Woosley's group, suckable collection of massive star models, hundreds of them. We've done 30 or so more. We've actually done 120 models, but 30 really good long-term 3D cell evolution models. There are effects of resolution. There's just so much resolution in a simulation. Neutrino oscillations. I'm not going to talk about that, don't worry. We don't know how to handle that properly. There are still remaining issues about the nuclear equation of state. Numerical techniques can always be improved, and ours is no exception. But what we've tried to do is bring together all the physics we can. And there's a lot of sophistication to this. It's not adequate, but it's pretty sophisticated, to watch and see what's happened, then try to understand what happened. So what are the basic features? And again, I want you just to get a sense of this. A new thing is that turbulence is important to the explosion mechanism. The stress of the turbulence that is generated in this context, and it's just neutrino heating from below, just like boiling water on a stove, actually contributes to the explosion. So the combination of the neutrino heating, just driving, and it's not momentum deposition, it's neutrino heating, and turbulence inaugurates the explosion. And for 25 or 30 years, we didn't see that. But now we do. It's basically a critical phenomenon. I'm not going to go into those details. The structure of the progenitor is crucial. All sorts of techniques have had to be developed in order to do this. But now the important thing is we're now able to do multiple 3D simulations in a year, 2 late times, with many model seconds, so that we can make many mistakes fast. We were not able to do that in the past. We were doing things 1D, 2D, a few models, maybe a 3D model in a year. There was a mistake, and so you had to redo it. Now, you can make a mistake 10% of the time and still see the panoply of results and draw general overarching conclusions from the synoptic view that is enabled by this particular capability. Okay, so what we get is correlations between the various observables, the explosion energy, the neutron star mass, black hole formation, this is an interesting topic, stellar mass black hole, the nucleosynthesis, the morphology of the blast. You can get induced spins. You can start out with no rotation and leave behind a rotating object. Isn't that interesting? Kicks, I mentioned. B fields. What is the origin of pulsar fields? Has anybody ever told you what the origin is other than flux freezing? This white dwarf has B field. You compress in, and that's it. That can't possibly be true. That is true, but that can't possibly be it, because it's all turbulent. And so you have a flux-frozen B field, and then the matter is just going to completely tear that apart. And you're going to get dynamo action. You have differential rotation. It's a whole new subject that needs to be addressed. Just to answer the question, what's the difference between a pulsar and a magnetar? And in what context? We're on the cusp of being able to address that. I'm not going to talk about that today, because I don't have a good answer. Okay, so the progenitor structures are important. This is something from Tom Weaver from many years ago from 87A. All I want to do is luminosity versus surface temperature, an HR diagram from a theorist perspective. And just want to call your attention to the fact that you could have an object explode as a red supergiant, as a blue supergiant, as a helium core in principle, all along here at a given luminosity. And each one of those looks different. And supernova observers have typed these things in different ways. Many of these are going to explode by the same mechanism. And so you have the same explosion happening in a different progenitor. It looks different. And we have to be able to correct for that to work back into the interior to understand the mechanism. Okay. So this is a density profile of the thing that just starts to collapse. Each one of those lines is one stellar model. This is 1,000 models from this collection here. And this is the density, 10 to the 10 grams per cubic centimeter in the center, very large. And then lower densities, this is the mass interior, that's the center. 1 solar mass interior, 2 solar mass interior. That's the Chandrasekhar core. And if they're all the same, it would be easy. But they're not. And you have those objects that look like this, so-called high compactness with a shallow slope. I'm going to use this term a lot. And then low compactness with a very steep slope. And then you do these calculations, the same models in the MESA code, and you get different results. Qualitatively, they're similar, but the mapping between ZAM's mass and final structure is very different. Why is that? I'm not going to go into that, but right now, that's part of the fact that the models have not converged. And so what I'm going to show you is assuming a profile, which for these people is a certain ZAM's mass, what is the result? Then I'm going to leave to the future figuring out how that profile maps into the ZAM's mass. And it's a function of metallicity. It's going to be a function of binarity, all sorts of things. I can't do all that. Okay. Now, you can plot various things, and don't worry about the details. Those that have followed some of the literature may recognize some of this. This is the compactness, that shallowness. The more shallow, more mass at a given radius, the higher the number. And if you plot and you just look at the dots, you get a non-monotonic behavior of this thing. And in the past, what people had said in ignorance is that the explodability was connected with the compactness. The steeper it was, that profile, that Chandrasekhar core, the easier it was to explode. That is completely false. They want a simple diagnostic to figure out explodability and what gives a neutron star, what gives a black hole. It's going to be much more complicated. In fact, down here, you can't get 10 to the 51 erg explosions in any model that anybody has, except for rapidly rotating ones. All these things are going to explode. People said these are all black holes. This is a black hole. This one I'm going to show you, at least in our simulations, which are the best but not the final word. This one explodes and leaves behind a black hole. Now, is that consistent with what I asked you earlier, your picture of what happens? Exploding object that leaves a black hole. We were always told they were silent supernovae. That was a black hole former. There may be a channel, but not all of them. Right there, here's a helium core mass versus this compactness, and you see this scatter. All these black dots are from this progenitor collection that we inherit and do the simulations for. The reds are models that we haven't been able to get explode. They're all in an island. I don't know whether this is true. This is just what I'm going to show you. I just don't know. And all these other models are exploding. And that one explodes too. And you notice it's the highest compactness model. Okay, so let's get into some of the results. From long-term simulations in 3D, 2D is different. When I was doing 2D simulations, I said it's adequate. Now that I'm doing 3D simulations, I say 2D is inadequate. Fortunately, there aren't 4D. Okay. Here's the average shock radius for a whole collection of models, again, from the Suckbo collection. And you can see these things explode nicely. Some of them don't. Some of them take a little bit more time. There's a correlation with the compactness and the density structure, which I'm not going to go into in detail, but I will talk about it on occasion. Here's on a larger scale. These things are exploding. We didn't make them explode. It emerged naturally, and the majority of the models explode for reasons we understand. So these are the types of simulations. That's a stalled shock. That's been the problem. The shock has been stalled. How do you re-energize that? This is just showing you the complexity of the hydrodynamics behind this stalled shock that we have to deal with. This is just a 0.15. This is 150 milliseconds after the bounce. And this is a stalled shock, but you can see the matter trajectories in the convective turbulent region behind this shock. That's driven by the neutrino heating. Again, boiling water on a stove. You're heating from below. The neutrino absorption is causing this to roil. Matter is flowing through here. It's a very dynamic context. You also have, and this is just a still, the central region. This is an isodensity surface. This is only about 100 kilometers aside. This is a neutron star at birth. It's not a sphere. It's convective in the interior, then it's radiative, then it's convective. You have all this turbulence on the outside. This is just a snapshot. But this is 3D, and this is during the Kelvin-Helmholtz phase, the cooling phase of the neutron star at birth. We're doing 3D stellar evolution for the neutron star. And this is the type of structure you get, complicated interior. I'm just trying to show the complexity of some of this. And this is just a movie. This is after bounce. Here's the shock wave at stall. Matter is flowing in. You can see the turbulence in here. This is the characteristic scale. Those are isoentropy surfaces. So you see bubbles forming, plumes, tendrils. This thing is exploded. We're zooming out just to confuse you. So this thing's actually exploding. But they explode generically in bubbles. And so you get very asymmetrical structures. This is one of the most spherical objects we get. And these are just stills. This is one of the most spherical objects we get. It exploded fairly early. It's a lower mass progenitor. Didn't have a time to get too asymmetrical. The longer you wait, the more asymmetrical it is. Then there are correlations all along the way. This is colored by nickel abundance. But that inner region is falling in. You get simultaneous explosion and accretion. And you can get accretion on one side and explosion more on another side. And that accretion gives you an accretion luminosity. Just GM over R m dot, right? Accretion on the surface. That gives you a component of the neutrino luminosity that actually helps power the explosion. In 1D, you can't have that. In 1D, you might explode and then you turn off accretion. And so you're turning off one of the power sources for the explosion itself. If you explode in 3D, you can keep the accretion going and keep the driving going. And that's what we see almost generically in core collapse. And doing it in 3D, it enabled us to see that. So it didn't turn itself off. Again, pretty asymmetrical. Stuff is falling in the interior and exploding on the outside. There's the shock wave. This is just an example. That's 3 seconds after bounce. I'm just going to show a few of these stills. There's where the neutron star is. Very asymmetrical explosion. You can imagine this has a high kick, 800 kilometers a second recoil. We observe neutron stars like that. I can't say that we have a perfect distribution of the final states. As I said, it's very progenitor dependent, our code dependent, but we're starting to glimpse the end of the light at the end of the tunnel. I could use a lot of, that's a terrible. And these are just a sample of the type of morphologies that we get for different models. At different times, but they're not spheres. There's always a dipolar component, quadrupolar, complicated, small-scale structures. 60 solar mass. People say 60 solar masses will leave black holes. This one left a neutron star. The mass loss in the Suckbold collection at solar metallicity was so significant that it left behind a 6 solar mass object. Started at 60. Mass loss may be wrong. People don't know the mass losses for massive stars. And what's in codes these days for stellar evolution is probably 3 or 4 times too high. That's one of the things that really needs to be done better. Okay. Let's see if I can, I got to do something with this. Yeah, it's going to freeze. No? It didn't freeze. Okay. This is just an example of a simulation, again. I like the final still, and so I thought I'd put you through the movie so you can see the final still. But you can see, again, these things are very complicated, and that emerges naturally. Dull color palette until, and you see the scale here. It's actually being colored by just density, mass density. But I like the way it emerges. Okay. And now, because we have graphic support, we take advantage of it. There's a techno version of this. You think I'm joking. So here's the shock wave. You see all the turbulence behind there. That's an isodensity surface in the center. That's that neutron star deep inside that's being birthed, and it's going through its Kelvin-Helmholtz phase, just shrinking. And at the same time that that's happening, the blast wave is coursing out through the rest of the star. There it is. And you can see it's accreting right over there in a wasp waste. That's the simultaneous accretion and explosion. The blast wave is always more spherical than the matter distribution. That's hydro. Okay, so let's look at some correlations. As I say, this compactness parameter is very useful in understanding what happens, but it isn't a predictor of explodability at all. We're going to look at supernova energy, the masses left behind, nickel-56 and titanium-44 ejecta, freeze out. There's a lot of different things, so let me get to that. This is the neutron star mass. This is the baryon mass of the neutron star left behind versus time. And this is logarithm of time. That's 10 seconds, 1 second, a tenth of a second. And this is colored by compactness, low compactness to high compactness. Look at the range of masses. We get neutron stars from about 1.2 solar masses gravitational to 2 solar masses gravitational. Depends on the nuclear equation of state. We don't have a final word on that, but it's pretty good. The stars are when the things exploded. And you notice these models. Every one of those dash models left a black hole. This is the most energetic explosion we've ever seen. It formed a black hole right there, exploded right there. And during that time, there was enough neutrino energy deposition that when it formed a black hole, it had enough to escape. And so there's timing. This one was accreting so fast that it exploded, and then it had no time, and this is giving a 37 solar mass black hole. This one is giving a 3.5 solar mass black hole, and this one is 2.5 solar mass. This is plot's not continued. These are neutron stars. And so you see there's a huge range of possibilities, but these black hole formers actually exploded. Some of them, they all want to explode. They all start to explode, and some of them are just undermined. The rug's pulled out from under them because the black hole formed too soon because the accretion rate was too large. Okay, so correlations. This stuff has never before really been shown. It's published, but recently. The neutron star gravitational mass. Here's 1.3 solar masses, 1.9 solar masses. This is the compactness, that shallowness. It's almost monotonic. This is a prediction. From a certain structure, you get a certain massive neutron star left behind. That's a prediction of the model. Now, maybe the slope is a little different. Maybe there's some noise in here. We don't know. But this is a prediction. This is one of the most important things to note. This is time, 1 second, 2 seconds, 3 seconds, 4 seconds. Again, most people stop their calculations right here. This is the total explosion energy. If you include the binding energy of the envelope that you have to overcome in the explosion, all the explosions start out with negative energy. They will explode, but they won't have enough energy. You have to keep driving them. And that's what's happening here. And you have to flatten out. These models have been taken out to about here. This is an old slide. You have to flatten out. Nope. Almost nobody has ever seen in the past these things flattening out. And that's what the new capability has enabled. Those are two black hole formers. They're the most energetic. We have a 100 solar mass model, this subsolar metallicity, that exploded very asymmetrically. And then the binding energy was just too large. It formed a new black hole really fast, and it was one of those aborted explosions. But it wanted to explode. Nature just didn't let it. No. Our code just didn't let it. But this is something that is really important to note. It takes time to asymptote to the final state. This is the explosion energy versus that compactness. Again, having to do with the slope. It's all correlated. It's almost monotonic. This is an explosion energy versus the time of explosion. The longer the time, the higher the explosion energy. People thought, well, if you explode early, you're going to be able to take advantage. Well, if you're exploding early, you don't have all that accretion luminosity to really power things. That accretion is slowing you down, but once it goes, it helps more than it hurts. This is the explosion energy versus the gravitational mass. Again, 1.9 solar masses, 1.2 solar masses, almost monotonic. The binding energy of the outside, exterior to 2 solar masses versus explosion energy, almost monotonic. These are the black hole formers. Almost monotonic, with a fair amount of noise. This is like a wind. For a wind, you have the asymptotic velocity is the escape velocity from the surface of the star. That's canonical stuff. Escape velocity is connected to binding energy per gram. Well, the more bound the outer envelope is, the bigger the explosion energy necessary to explode it. But also, the larger the binding energy, the larger the accretion rate, which helps you in the luminosity. Asymmetry. This is the mass dipole asymmetry. Just the asymmetry in the explosion in some measure. Versus explosion energy. The larger the explosion energy, the more asymmetric, with some scatter. Okay, so there are lots of myths. I don't know if I want to belabor these. I won't. So in every one of these contexts, when you get an explosion, the neutron star has a pressure around it that progressively decreases, right? You want to get an isolated neutron star. But what it turns out is that you get a wind that emerges. It's like a Parker wind. The old Parker wind was thermally driven. And it turns out that the numbers work out perfectly so that early in the explosion, there's another explosion. There's a wind that comes out, and it moves at 40,000 kilometers a second. And then hits the inner debris, and it helps with about 10% of the energy of the explosion. And that's the wind that many people for decades thought was the source of the R process. We don't see that. We see the first peak. Maybe with rapidly rotating bipolar jet explosions with magnetic fields effect, you might get that. That's in the literature. We don't know that yet. But here are the winds. These are mass trajectories. So stuff falls on, it settles there, and then look, that mass zone just jumped off. That's a wind. This is the shock wave, the early shock. This is the primary shock wave, and there's a lot of nucleosynthesis behind there. This is colored in velocity. That's 45,000 kilometers a second. That's 15,000 kilometers a second. Was that in your picture? A secondary explosion. We see this for every model. Nucleosynthesis is an important aspect. The material that's ejected has a certain neutron richness. That neutron richness is affected by the neutrino absorption and the anti-neutrino absorption. They fight. You have to get the spectrum right. I don't know if we're getting it right. We're getting a pretty good estimate. So you have to get the spectrum of all these species as a function of time, et cetera. And symmetric material is at 0.5 electron fraction. That's the same number of neutrons as protons. That's what oxygen-16 is. That's what nickel-56 is. Titanium-44 is. All those are alpha nuclei. Most of the stuff that's ejected, this is a log plot, is near there. But you see proton richness and neutron richness. And most of these models are proton-rich. It's this stuff that would have given the R process. In fact, you got to get down here. But we get some neutron-rich stuff. We get the first peak of the R process, but not for all the models. You can see how rich it is. Each one of these lines is for a different model. And it depended on how it exploded and how quickly it exploded and this fight between the neutrinos and the antineutrinos. That's a detail. I'm not going to go into it, but I just wanted to mention. Nickel-56. The nucleosynthesis of nickel-56, which is an important component of supernova explosions. We see the nickel. It's heating up the late time light curves. It's measured some of the time. It takes many seconds to asymptote. Some of these models still haven't flattened out. But we can predict this is, so this is 0.08 solar masses, 0.06 solar masses. We can get the basic numbers. There's an 87A was right here. The lower mass ones asymptote quicker with lower nickel yields. Higher mass ones asymptote much later with higher nickel yields. It's all part of the systematics that we see, that we wouldn't be able to see if we did one model in 3D in a year and made a mistake. Okay. Yeah, all these correlations. This is the nickel mass versus explosion energy. The higher the explosion energy, the greater the nickel yields. And that's a very good correlation. The actual slope will depend on the progenitor model and us. But this sort of correlation is dead on. Now, this is a scatter plot of measurements of both these things. You can't measure the explosion energy very well, unfortunately, yet. The nickel mass is a little bit better measured. Our models just go through there. We don't know what the scatter should be. I don't know how much this scatter should be believed, and I don't know how much our model should be believed. But the two things that may not be believable correspond. Titanium, titanium-44. This was observed using NuSTAR in Cas A. Cas A, 350 years old. The mean life for titanium-44 radioactive decay is 80 years, so there's some left. This was the distribution. Here's the iron distribution from XMM. Here's a lot of iron here, a lot of iron here. People thought that the iron and the titanium were produced in the same places. Look at this. They're almost in opposite places. There's a hole here. Now, the angular resolution of this is terrible. It's not as good as this picture. But qualitatively, there's something. Well, titanium-44. People stopped the calculations right there. You have to calculate for 10 to 15 seconds in order to get what the titanium-44 abundance is. And it's only in 3D simulations you see this. When you try to do nucleosynthesis with a bomb, put a bomb in the center of a massive star, which is the entire tradition of nucleosynthesis for the last 50 years, you can't get this. It's a 3D effect. And we published a paper at AppJ on this. Tianxu Wang in particular, I didn't put his name on there, was instrumental in this. Okay. We do get higher A material stuff. And these are different models. Some are flat here. This is if it were flat, it's all solar. But for this collection of models, we get some very interesting nucleosynthesis. I don't want to go into the details. But here, a couple of models provide the first peak of the R process. Many of them don't. And that has to do with the electron fraction and the neutron richness of the ejecta. And that has to do with the character of the hydrodynamics. And we see the one-to-one connection. All right. All right. So this is that very asymmetrical explosion. This stuff, you see this stuff falling in? Maybe, oh, there's another one. This is just, these are trajectories of parcels of nickel-56. We did 320,000 trajectories for each model to figure out the nucleosynthesis. And you have to follow each one of them. Some of them go inside and they come out, et cetera, and it's pretty messy. Because this is a nice graphic, I thought I'd share it. Same sort of thing. That stuff is purple is not nickel. It comes out blue and yellow. It is nickel. You can see the transformation of purple to yellow is that nucleosynthesis. The stuff that wasn't nickel-56 is stuff that is. And it's coming out in complicated trajectories. We didn't want to map the interior because it's a real mess. Now this is one of our most symmetrical explosions. There are always going to be nickel bubbles. There are always going to be these small structures. And as you go up in Zamzas, mostly compactness, you actually get larger structures and more asymmetrical explosions. That's a theme. And there's the blast wave, much more spherical. I just like this. And so in some of the models, for example, we've carried out the calculation to much later times. We can't do it with our Fornax code. It's just too expensive. Microsecond time steps, you want to go hour scales, day scales. So we have to map it. And in mapping it, we get stills like this. The nickel is in here. That's this stuff here. You see that bulbous thing here? That's that. The oxygen is here. You see that hole there? That's that. The nickel breaks out of the oxygen shell. The nickel and the oxygen in the inside was converted into the nickel. But it broke out in different ways. And the nickel, in fact, can get outside the oxygen region. It can go ahead of the rest of the matter because it's a little denser. You get nickel bullets. We're seeing that. This is a simulation to much later time. There's our Fornax calculation mapped into Flash. You see these instabilities at the hydrogen-helium interface. The time step goes up. That reverse shock converged at the center, off-center. We started out spherical, but it was so turbulent when it converged in the inside, it didn't converge to the neutron star that was left. And that hit the surface of the star. That's after 4 days. Okay. This is our most spherical model. At the same time, because of the asymmetries, you get kicks. So you can calculate what the recoil is. And here's our total kick, the absolute value, versus time. And you see it takes time to asymptote. Some of these haven't even asymptoted. But we get 1,000 kilometers per second. These black hole formers, which are exotic, are kicked with huge speeds. They are in the so-called low mass gap of black holes that's observed by X-ray sources. So we produce them. But these are going so fast you can't keep them in binaries. So that channel will produce gap black holes, but you won't see them. That could be the reason for the gap, but I don't know statistically. But we get a whole range of kick speeds. And then there's a correlation between the pseudo-correlation between the neutron star mass and the kicks. The important thing is the low mass neutron stars all have small kicks because of the low degree of asymmetry. The higher mass ones are scattered all over the place. I don't know what's real here because there's a lot of stochasticity. We haven't gotten the distribution functions of these things. But we get the range of observations. The average values in here, the average observed values in here. And that's, of course, weighted by the distribution. So these may be there, but there just aren't as many stars at high mass as there are at low mass. Just the saltpeter mass function. Yeah. The kicks and the explosion energies are roughly correlated. Roughly correlated. Higher the explosion energy, the more oomph you have. If you have some asymmetry, you get kick, and the higher explosion energies also have more asymmetry, so it all goes together. Let's see now. Curiously, all these models start out with no spin. We know that that's not true. But they're left with spin. Conserving angular momentum, the stuff that's ejected has a little bit of angular momentum. There's angular momentum left behind. Stuff falling back has impact parameters. There's a net angular momentum being brought back from the infall. And you can get spins, well, this is angular momentum. You can get, you can get spins that could be very low. This is 1 second. That's not really fast, but that's 10 milliseconds. You can get a range. This is the most stochastic thing in what we're doing, as far as we can tell. You get impact parameter positive, impact parameter negative, impact parameter in the middle. We don't know what the distribution is. We just know that this type of thing can happen. Now, we get 4 different channels for black hole formation, only one of which is silent. And even the silent one is probably not silent. Imagine, in your mind, your picture from before, failed supernova. Whole star is gobbled up. A little bit of angular momentum, you really think a little bit of angular momentum going from the Jupiter's orbit down to the size of Cambridge is not going to give you disks, is not going to give you jets. We just don't know the magnitude of this. But it's really hard to think theoretically of any silent supernova. the neutrino mechanism just may fail. And then things are gobbled up. But we actually get 4 different channels of black hole formation. I showed you this. One channel is it doesn't explode, and then you accrete all that stuff, and you'll have secondary explosions and this sort of thing. We don't know what the energies are. They're probably pretty subdominant. This I showed you before. The dash curves, these are the ones that didn't explode. And we haven't carried them out any further. They've been carried out to 2 and 3 seconds, and we've never seen, it's possible they explode at much, much, much later times, but we've never seen anything explode after a second. So we generally stop the calculation. And these we wanted just to continue to see whether anything happened. Almost everything else explodes, though. These are still accreting stuff, but there are these other channels. This was a 100 solar mass one I mentioned before. It tried to explode. That time interval was too short. Binding energy was too large, 37 solar masses. This one, that's enough of an interval. Energy of the explosion, 1.6 times 10 to the 51 ergs. Black hole mass, 3.5 solar masses. This one, much longer time to black hole formation. That's black hole formation, black hole formation, black hole formation. That's 2.5 times 10 to the 51 ergs. Very asymmetrical explosion. We don't know how many of these models at these higher compactnesses do this. But we're getting that as a channel. And this is just high compactness, high-ish compactness, very low compactness. These all explode. These don't. These all explode. These explode and leave behind black holes. Very massive black hole. This is a pair instability supernova. But it left behind it tried to explode. I don't have a good slide for that. We're trying to write a paper. We're almost finished with the calculations. And then hopefully we'll get this out. This is, again, the same as I showed you before. This is the shock radius versus time. And some of these explode very easily. And then they're later and later and later. They're colored by that compactness. And so low compactness, higher still. The time of explosion is not monotonic with it. The really high compactnesses explode easily, and these leave behind black holes. Whether this is true is another matter. So I want to show one example. This is the 40 solar mass model I referred to before. Here's the lapse, the gravitational lapse. That's the redshift from the very center. And when that gets really low, black hole forms. Unfortunately, when the black hole forms, our code crashes. And so we put a point mass there for the black hole, and we put a boundary condition, and we follow it. In our code, we followed it for 21 more seconds. But if we really want to go really far, we've mapped it into Flash, and that's gone out for 4 days. But we don't have a lot of models to show on that yet. Here's this model. Here's the average shock, the maximum shock radius. Here's the time, quarter of a second. Then it starts to oscillate. That's the so-called spiral standing accretion shock instability. It almost never shows up. In the models that explode easily, it's not there. If you do it in 3D, you don't see it. You saw those in 2D. That was an artifact of the 2D simulations of the past. It's really not important until later times. When the thing is starting to fail, then this instability occurs. It increases the so-called gain region. It allows you to see lower ram pressures so that it's less confined, and it blows up very asymmetrically. And that's the oscillation. Here's the one that failed completely. It still oscillates like that. And it modulates the gravitational wave signature and the neutrino signature, AM modulation. This is the blast wave. That's stalled shock, settles down, and look at that oscillation. That actually kicked it into explosion. Look at the accretion. Very asymmetrical, but this is still blowing up. The color, yellow and red, is high entropy, and the other colors are low. Hot stuff is red, and you see what emerged. These are bipolar neutrino-driven jets. The thing that was left behind was spun up, so it's oblate. That's why you get the bipolar neutrino driving. That black dot, that was the black hole forming. The blast is still continuing, though, even though it's not being driven, because it was driven enough. That has to do with the duration. I think that's cool. Yeah. All right. If I end on this, Of course, in all these contexts, you have neutrino signatures that are going to be incredibly diagnostic of the internal dynamics of the explosion. Unfortunately, we have to have a galactic supernova. For gravitational waves, it's starting to become an interesting, nuanced subject. And so I want to give a little bit of indication of the gravitational wave signatures, and I'm sure Jasmine has talked about this in context. I want to call out Lila Choi, who is an undergraduate at Princeton, and we've just published an AppJ paper on some aspects of this. And she's going to do her senior thesis with me. She was a junior. If she applies here, do not ignore her. Maybe this thing is... Oh. That's just to show you the noisy signal from all the stochasticity, the stuff raining in, is causing the inner region to shake. It's the source of much of the gravitational radiation at high frequencies. These are different models. This is time, different times. This is out to 6 seconds. This is out to a few seconds. It's different for different models. So we can explain these different phases, but it looks like a mess until you look at a spectrogram, frequency versus time, and you look at that. It's astroseismology. What's happening is the plumes are hitting the surfaces and is causing the F mode to ring. And that frequency is changing because of the Kelvin-Helmholtz contraction, the cooling of the neutron star. Frequency goes up. You also get some interesting effects here. Anybody who knows about quantum mechanics, that's an avoided crossing, where the quantum numbers are the same. This is classic astroseismology. It's just that normal neutron stars that we look at don't have exciters that can really give you these high amplitudes, but at this formation of the neutron star, it's a really violent context. And these things are hitting the surface. Remember, fallback, infall? And you get these sorts of things. And as I indicated, there may be noise here, but there's an underlying structure. I'm going to do it at the end. And if you could extract that, you can get a lot of information on the neutron star at birth and its evolution. That would be cool. This is a diagram. Look at there's a dot here, dot here, dot here, dot here. It's a straight line in a log-log plot. This is the energy at high frequencies, kilohertz, hundreds of hertz frequencies, versus compactness. That density profile, again, tells you at high compactness, you get a large amount of gravitational radiation. At low compactness, not so much. There's a theme here. I just don't know the compactness ZAMS mass mapping. And you get all sorts of structures. But notice this, zero strain. They leave behind a non-zero strain. It's called memory. The metric is permanently altered when the gravitational waves go by you. That's been happening with the emerging black holes that LIGO has been seeing. There's a net memory effect. It's just at low frequency. See, if you Fourier analyze, the thing goes from here to here. That's a low frequency component. LIGO can't see that. There's also a neutrino component. This is the amount of energy radiated. It's not very much compared to neutrinos. It's systematic with compactness and progenitor. But if you actually calculate the corresponding effect of the neutrinos themselves, think about it. Neutrinos are going at the speed of light. There's 1/10 of a solar mass being radiated, and it's asymmetrical. That's a time-changing quadrupole moment. But it's at low frequencies, out of LIGO band mostly, not completely. But look at the size of these signals. If you were paying attention, the strains that we see here in these units, for the matter, got up to about 10. 3, 2. These are getting up to 1,000 due to the neutrinos at low frequencies. That would be amazing. It's because the next slide is so big. I did press the button. If I press it again, we're going to skip it. I don't care. Oh, see? All right. So these are the types of ranges you can get. These are kiloparsecs for advanced LIGO. That's more than I would have expected. And that's just for simple detection, not characterization. That's something for the future. And this is much larger than we had. This is the spectrum. Here's 10 hertz, 100 hertz, 1,000 hertz. Look at all that. These are different models. Each one of the colors is a different model, more or less in compactness. You see bumps. We can understand the bumps. This is the LIGO sensitivity curves. This is Cosmic Explorer and Einstein telescope, the 3G suggestions. And this is Desigo, the Japanese suggestion for space. It's not LISA. LISA's over here on this plot. But look at the difference. This is for the matter. This is for the total. Here's neutrinos. The neutrino memory effect at low frequencies dominates. And if you could put together a detector like that, that difference right there says you could see out to megaparsecs. I was once offered $50,000 extra on my NSF grant if I could show that you could see gravitational waves out to Virgo. I couldn't do it. I couldn't do it. I still can't do it. But it's getting closer, which is amazing. So I hope I've communicated to you that there's been some progress in the field. In my estimation, in fact, the problem is qualitatively solved, but not quantitatively solved. We have our work cut out for us. But there's a real chance that the theory of supernovae, which has taken 60 years to develop, is starting to merge in a productive way with the larger astronomical community that's being discovered supernovae in profusion, thousands of them. And this merger of the two different approaches, observational and theoretical, I think will bear lots of fruit. And what do we predict? We have many predictions, as I've said. There are many details here I could read off. There are many ambiguities. But the major thing is in 3D with neutrinos, including the turbulence, explosions seem pretty natural. We're starting to get a sense of what gives us black holes, what gives us neutron stars. It's not your father's theory. It's a theory for the future. And I think with that, I'll leave it with you. Thank you.
Thank you. Thank you very much, Dr. Burrows, for such an excellent talk. I'm just going to give folks 10 seconds for your brains to cool down a bit. But do we have any questions?
And you didn't think I was...
Yes. Thank you so much.
We don't have to show. No, it's the same movie.
Let it play.
Normally, I determine the movie on the basis of the audience. Think of this as a compliment.
Okay, so we have our first question.
So hi, Adam. Excellent talk. Excellent explanation of asymmetric explosions. But can you explain the symmetric ones now? We have Kepler, we have 1066. There are a whole bunch that look almost perfect. But with all the turbulence driving this model, that becomes almost unimaginable.
It depends on the progenitor. We really don't know what it is. But you're absolutely right. The thing that bothers me a lot is that there's a spectrum of behaviors. And I don't know what that is. I don't know how common Kepler is. That remains to be seen. And some of what we say may be wrong. But I would bet that some of these correlations are going to survive in the future. But you have to have the statistics. And it's not a simple back-of-the-envelope calculation. I can't give you power laws that will explain things. And that has been one of the real problems in this theory. It is detailed and complicated, and it's hard to communicate some of the essence as well as the products. But you're absolutely right. We have to do better on the distribution function. For a given progenitor, you're going to get a distribution function for energies. We don't know what that width is.
Any more questions?
Okay.
Are any of these
Please.
stars rotating?
They are definitely rotating, but we haven't rotated them. So you're absolutely right. And one of the reasons we didn't do that is that it's just too many degrees of freedom. And that has to be done in the future. Now, there have been models that have been performed by other groups. They don't calculate as long, but they do include rotation and magnetic fields. And sometimes, if they're rotating fast enough, and we published something in 2007, but that was only in 2D with rotation. If they're rotating fast enough, you can get bipolar neutrino-driven, bipolar MHD-driven jets. And we think that that is also connected with long soft GRBs. That 40 solar mass one I showed you was spun up fast enough that even without initial rotation, it was rotating fast enough to give you a GRB. We just haven't simulated it with B fields. And that's one of the next things we need to do. We need to incorporate neutrino oscillations as best as possible, and we need to do a whole range of rotating models. We just don't know what the internal rotation is like. But this is an important aspect. If it's rotating slowly, I don't think it makes much difference. Slowly is a matter of definition. So, good question.
So, Adam, I mean, these calculations are really impressive. Are there fundamental things that have changed that have enabled these longer calculations?
Oh, that's a code question in some sense. Yes, in the past, well, first there's more supercomputer power. That has been useful. And then you have to get access to it. That's important. But our code is not perfect, but it has addressed all the bells and whistles except neutrino oscillation and initial rotation, although we can do that. We just focused. The big thing was that we can look at what goes into those calculations, and in the past, people had done, this technical term, fully implicit calculations for the neutrino transfer because there's a light travel time limitation. So if you do real radiative transfer and you worry about the speed of light, then you can't have a time step that is longer than the light travel time across a zone. If it's done explicitly, which is the default thing to do. If you do it implicitly, then you get an iterative solution, which means the solution at one point has to know about the solutions at every point. And you iterate the entire grid of 33 million zones, every time step, to a solution. You have to have that because the spatial operator in the transport equation is a derivative. That means that the zones are coupled. So you need to solve this one and this one and this one all together if you do it implicitly. That is expensive, and it doesn't scale. And so because it was expensive, and because you can't scale it to more and more processors to try to compensate for other limitations, that slowed people down a lot. What we were able to notice, which is sort of stupid in retrospect, the light travel time across the zones is similar to the sound travel time in the center. The sound travel time in the center is the Courant condition, which is the condition for explicit hydrodynamics. You have to keep the time step low or there's a numerical instability. We were already doing okay with the light travel time of the zones on the outside, so we didn't need to do it implicitly. That sped up the code by a factor of 5. And it's now 10 times faster than anybody else's code. And we also got GPU version working. Most of these simulations were done on GPUs. And that gave us a factor. It's not as much of a speed up as I would have liked, but it gave us about a factor of 2.5. And so we can do 3D simulations that would have otherwise taken a year or two in the past. And other groups are going to start doing this. And if they can speed these things up, and we're going to have a lot of interaction and cross-comparison, et cetera. There have been some cross-comparisons, but not full 3D. It's turbulent. So how do you compare? That's a problem in 3D turbulent hydrodynamics in all. How do you take the difference of two different simulations that should naturally be different and say that they're the same? Yeah.
So this is already terrific, and so my question is going to go back to what Scott was saying, and it's possibly unfair. So if you look at something like Casset, 350 years after this, do you have any idea whether the asymmetry that you see, after 7 seconds or whatever is connected to 350 years later?
Well, no. This is a topic of important current research because the blast waves are going to propagate. As I showed one particular model, blast waves are going to propagate through a star, and there are other instabilities that are going to mix things up. And so the morphology that we see in the first 10 seconds is not going to be the morphology that you see asymptotically. But we're going to start out with asymmetries. We're going to start out with nickel bubbles and bullets and this sort of thing that will then propagate through the star. And the complications, the many simulations that we'll do that will give us a broad spectrum of possibilities will inform our comparisons with something like Casset. What we will say is something like Casset, the structures are exactly what we do expect. The asymmetry in the iron distribution that XMM saw many years ago is exactly the type of asymmetry that we get in many models. We just have to be able to extract from CAS-A, for example, the detailed element nucleosynthesis, the real explosion energies. It would be very nice to be able to, there's a neutron star at the center there. It'd be nice to be able to find some way of estimating its mass. We don't have good techniques for that. There are lots of things like that. And it's one supernova remnant. I'd be happy if I could look at all supernova remnants and get a distribution of their properties, and then I get a distribution of my properties, and the distributions look similar. But you want me to explain each individual supernova remnant? I don't think I can claim I can do that.
And with that, just one last question.
Very interesting talk. So that's what all of the stochasticities. I wanted to know, is there any particular process that identified the direction of the explosion versus the direction of accretion? And that's like analog to galaxy feeding feedback processes and symmetries involved?
It's hard to figure out ahead of time, given a spherical calculation, actually what direction. We can see during the hydrodynamics why it went in one direction, but why it pointed out that way. Remember that oscillation of that black hole former. It was collapsing in, and then it was like this. Well, the shock experiences different radii in doing that, and there's a maximum radius, and it's pushing into the flow that will have a smaller ram pressure at larger radii. And what we frequently see is, for those particular models, it sees that lower ram pressure, and that's the preferred direction to explode. But we can't figure out ahead of time because it's just, I haven't been able to figure out ahead of time. When they're rotating, though, the suspicion is that the rotation axis is going to help us. We just haven't demonstrated that. And we don't know how fast they have to rotate for that to help, because the slow rotators aren't going to make a difference.
All right, well, and with that, one more round of applause, please, for our speaker. Thanks. And yeah, refreshments at the back.